Okay, everyone, let's get started. Got some stuff I need to cover today. Any issues with lab 2? Seems like everyone had a pretty easy job of that. Exam grades were good. I'll just quickly go over the exam questions because the final will be comprehensive. If you have any questions, let me know. Then I'm going to talk about the next lab, which I'll assign today, and then I have some conceptual material I have to get through in the next few lectures. Okay, so several of these questions had 100% correct rate, so I'll skip those ones. So question 1, 70% of you got this one right. It asks what CPUL and CFA and the SPI transaction shown below. CPUL's really easy to find. You just look for what the clock starts out at. CFA, on the other hand, is a little bit more tricky. The way I remember it is I look at the clock as compared to MOSI and MISO. And if MOSI and MISO have a head start by half a clock cycle, in other words, push to the left relative to the first edge of the clock, then CFA is 0. So I think in this case, I think they're both 1. Yeah, I don't know the answers. I think that's right? Okay, question 3, 94% of you got this. Assume a CPU has an interrupt handler that requires 50 milliseconds to execute and whose interrupt controller is rising edge triggered with no acknowledge. What's the shortest amount of time between consecutive interrupts that will cause the CPU to miss the second interrupt, assuming the CPU lacks the logic to keep track of outstanding interrupt requests? So in this case, if we have 2 interrupts that are issued within the time it takes to service the first one, then the CPU could miss the second one. So in this case, it would have to be faster. You'd have to have 2 interrupts within 50 milliseconds, right? Okay, question 5. A device connected to a UART channel with even parity receives the value 6, 7, and hex, including the parity bit, but not including the start and stop bit. So that 6, 7 is meant to just be the data and the parity. And so you have to count the number of 1 bits in that hex value. So 6 would have 2 1s and 7 would have 3, right? So there's 5 1 bits in there in total. And so if there's even parity and you have 5 1 bits, and there must have been an error, right? Hey, which side of the I2C channel has control of SDA during the time in which the SCL signal is high for the 18th time? So 18th time would be the acknowledge for the data part, right? And so if you're doing a read, then the acknowledge would be on the master side, right? Because the master would be acknowledging the data coming from the slave. And on a write, it would be on the slave side, right? So for a read, it would be master would be acknowledging, and for write, it would be the slave would be acknowledging. Which of the protocols uses a level-sensitive clock? I was surprised at this question. 64% got this correct. I'm not sure, I don't know if maybe this was confusingly worded. So level-sensitive means that it uses like a latch-based system, right? So the only one that we talked about that does that is I2C, right? JTAG and SPI are edge sensitive protocols. Make sense? And UART is asynchronous, so I didn't put UART here. So I2C. Suppose SPI bus has 10 attached slaves and 1 SS signal. If it has 1 SS signal, it must be doing a daisy chain like JTAG. So how many cycles are needed for the master to exchange 8 bits with all 10 slaves? It would be just 8 times 10. This one, 90% of you got this one right, and I actually thought this one would be hard because I didn't really spend a lot of time on JTAG. It says in JTAG, what state is entered for the following sequence on TMS? So generally with JTAG, you're going to start out with at least 5 1s at the beginning because that guarantees that you start out in this start state, this reset state after the 1s, and then. So then after that sequence of 1s, we'll go 0, and then 1, and then 0, 0. So it should be shift IR, right? Okay, this one was 70%. This was a tough one. assuming there's 5 devices attached to a 3.3 volt shared open drain signal of which none are pulling down. So if none are pulling down, what that means is that you have 5 parallel resistors that are going to be the off resistance of the transistors, right? So if the transistors aren't pulling, that means they're not like turned on, they're not connected, right? But usually, typically, transistors are modeled as ideal switches. So if they're not on, you just assume they're an open circuit, right? But in reality, when a transistor is not on, it's not an open circuit. They have basically just a lot of resistance, right? So in this case, I'm saying 5 mega ohms is the off resistance. So if you have 5 transistors that are all off and they're in parallel, then it would be a parallel resistance or equivalent to 5 parallel 5 mega ohm resistors, right? And so that would be 1 over 5 mega ohms, right? Would be the equivalent resistance. But then you also have a load. A load means that on that bus, there's a resistive load, which is another parallel resistor. Maybe this is what was confusing about this. It was a load resistor. So that one was adding 500 kiloohms. That was the load, okay? So the equivalent resistance of all the parallel resistors would be 5 mega ohms and 1 500 kilo ohm, right? Which is 5 million divided by 15, right? If I did the math right there, right? But then it gets a little bit more complicated because I ask you what the voltage is that's formed by the voltage divider, where you have a 10 kilo ohm pull-up resistor and then this on the other side. So I'm asking what the voltage is on the node that's between the pull-up resistor, right, and then this resistor going down to ground. So this is a voltage divider, right? So you have to remember your electrical engineering for this. So the voltage divider would be 3.3 volts, which is your supply, multiplied by the whatever's between the voltage, the voltage between the node you're measuring and ground, which is just this, right? And the total resistance, right? Which is this plus the 10K, right? So what ends up happening is you end up with 3.2 volts. So you get a 100 millivolt drop caused by that voltage divider, okay? Which, you know, it's not, I mean, not a big deal. It's not going to hurt anything, but you do get a drop. The point is that there is a price to pay for this open drain. It's not free. How many wires are needed for UART? How many wires are needed, including ground? 3, right? Oh, this one, 40%. What can you infer from the SPI transaction shown below? I mean, the idea was that you just look at MISO, right? You can see MISO is sending something back, so it must be a read, right? So I think that was the lowest. That was the hardest question on the exam, statistically. Peripheral has a base IO address of 100400 with a size FC00. What's the highest byte address? Basically, just add them and subtract 1. Consider the I2C transaction below. What portion of the transaction was not acknowledged? Okay, so for this, the acknowledge you have to count, right? So it's the 9th and the 18th cycle, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that was acknowledged. 1, 2, 3, 4, 5, 6, 7, 8, 9. That was not acknowledged. It was the data, right? It was the second 8 bits was not acknowledged. We don't know if it was the master or slave that was not acknowledging it. I mean, we could probably figure that out, but I don't really care. I just can see that the data part is not acknowledged based on the fact that the 18th bit is high. Or the 18th bit the 18th SDA bit is high. Assume the SPI channel has CFA 1 and C-pole 0. What event occurs during the first rising clock edge? So rising clock edge. So the first clock edge is falling, right, because CFA is 1. And, I'm sorry, no, C-pole is 0. So the first edge is rising because you start out with 0 in the clock, right, because of C-pole. And then because CFA is 1, what that means is you're going to wait till the second edge to do something, right? Right? See, to me, this is the hardest question. I always have to think about these ones. And yet 97% of you got this right, but only 40% of you, I don't get it. I don't know why this one, why'd you guys have such an easy job with this one? And yet, see, this one I have to think about. Like, okay, so what happens during the first clock edge, then I think MOSI and MISO must be changing on the first edge because you're supposed to sample on the second edge, right? Why? Just because of CFA, right? So C-pole is kind of, we don't care. This question doesn't actually require you to know what C-pole is, right? Who cares what C-pole is? The question is what happens on the first edge? Well, on the first edge, we're in flux, right? Because the second edge is where they're stabilized. The data is stable, right? So I don't understand how 90.
There's really only 2 answer periods. Either sample or.
Oh, you're right. Yeah, but it wasn't like it was a 50% success rate. You guys got 97%.
No, because we were like, if it's before our reading edge,
yeah,
it has to be eventually changing. But yeah, I guess you're right. I guess we just all.
I'm just
looked at it. I mean.
That still blows me away, that 97% on that one. Okay, this one was hard, 64%. Suppose a UART channel has a baud rate of 57,600, use 8 data bits, 1 parity bit, 1 stop bit. So that means we got 8 data bits, but the total bits are 8 plus 1 parity, that's 9, plus 1 stop is 10. But then there's the start, that's 11. So you only get 8 out of 11 bits. So 8 elevenths times 57,600, which I guess is, I don't know, whatever that turns out to be, right? 41,000, yeah.
Yeah, because I forgot about the start bit.
Yeah. Okay, that was the trick here. The start bit wasn't mentioned.
I don't think people got the trick of needing to look at only MISO on 14 that we messed up on. I think that was part of the problem. Like we were looking at MOSI and MISO.
Yeah, oh.
That's why 14 was so low.
Yeah, that's why.
Oh, okay. Oh, okay. Yeah, it could be.
We saw information going across on MOSI, so we
yeah.
Oh, that's.
But this one should be part of the header, right? I think, right? 1, 2, 3, 4, 5, 6, 7. Yeah.
It was just like we thought it was this is easy. There's data going across both, so it's an exchange instead of just looking at MISO like we should have.
Oh, okay. Oh, an exchange. One exchange. So there's 2 exchanges technically.
So
yeah.
Defaulted, one exchange.
Gotcha. Okay.
I think that's what most people.
Yeah.
Okay, that makes sense. And then question 20, I skipped questions 18 and 19 because that was 100%. Those are 100%. And then that was it, right? Yeah, 20. Good, perfect. All right, so that's all there is there. Next item on this agenda is Lab 3. Okay, so Lab 3 is going to be, there's going to be a big jump of difficulty, just to warn you, between Labs 2 and 3. 3 is significantly harder. So there's 2 reasons for that. One is that we're going to interact with 2 peripherals this time at the same time. So you're going to have to write code that manages 2 peripherals somehow without an operating system to do your system management for you, like normally computers do, right? So this is going to be bare metal management of 2 simultaneous concurrent peripherals. And the other thing is that you're going to write the driver now this time. You're not going to use the any kind of driver support from the Arduino framework. You're going to write low-level code. So all of the code in this lab, or all the interaction with the peripherals, is going to involve control and status registers, right? Writing to registers, reading to registers, bit twiddling, right? And there tends to be a lot of that when you write a driver. And so this lab will give you an idea of how much of that kind of bit-level interactions you have to do to actually implement a driver, right? Because when you write an Arduino, you get kind of this false sense where you can write one line of code that that does a lot of I/O behind the scenes. This will give you an idea of what's actually going on. So you might say, well, why are we doing this though? Is this just a hazing ritual or torturing us, or what's going on? Well, as it turns out, one of the peripherals, the remote control transceiver, doesn't have a driver. No one in the world has ever made an Arduino wire library for this, which seems very unlikely to me. But apparently, according to Alex, that is true, right? The LED controller, I think there might be one for this, but you're not allowed to use it. Just like you weren't. Now remember, there was also an I²C library that you could have used for lab 2, right?
Yeah.
But we didn't use that.
That's right.
But we did use the GPIO library, right?
Yeah.
Okay, anyway, so we're going to use 2 peripherals. One's called the remote control transceiver, and one's called the LEDC, which I think stands for LED controller, I think, LEDC. So the remote control transceiver is designed to create a waveform. It's designed to communicate with infrared remote controls, which nothing uses infrared remote controls anymore, which irritates me because when the remote control to my TV gets stuck between my couch cushions, the TV starts freaking out because you don't have to point it at the TV anymore like it used to when I was a kid. Of course, you guys might have never even experienced having to point a remote control at a TV.
Bro, I had to get up and freaking turn.
Oh,
Yeah,
okay.
So let's see our TVs as kids.
Okay, so this is designed for a non-existent technology, infrared remote controls, because infrared remote controls use something called Manchester encoding. And the idea is that this is yet another protocol that is an asynchronous protocol. So if you have an infrared remote, you can't send a clock. There's no clock wire, so you can't have a synchronous protocol. So we got to go asynchronous. So your choice is you could use something like UART, where both sides just agree on a clock, but that would be very slow and also would be even more unreliable than UART, considering that it's a wireless technology. It's infrared. Or you could try to extract the clock signal from the data signal, which is what PCI Express does. And as it turns out, that's the option they took for this. They use this thing called Manchester encoding. And so basically the way it works is to encode the signal in Manchester, it's very simple. You just have a clock and you XNOR it with the data. Done. Very simple. However, to decode a Manchester encoded signal, that's tricky. So what's happening here basically is that if you look at what's happening, a 1 in the data stream is a falling edge, and a 0 in the data stream is a rising edge, right? So that's fundamentally how it works. But then how do you decide where to sample on the receiving side? Well, that's unclear. I still don't know how that works, right? But the point is that you got a lot of transitions in here, right? So if you send a bunch of zeros, you're not going to just have a flat line going over the infrared channel. You're going to have just as many transitions for a bunch of zeros as you would for a bunch of ones or a bunch of mixture of ones and zeros, right? That's the idea behind Manchester encoding. Now, in infrared, just so you know, in addition to Manchester encoding, infrared signals also are modulated on a 38 kilohertz oscillator. So what's happening is that when this Manchester is 1, it's not just 1, it's actually just an oscillating signal. And when it's 0, it's a non-oscillating 0. So basically, for an infrared control, you modulate the Manchester encoded signal on top of a carrier signal, which is something we don't have to worry about, but is supported in the RMT. We just turn that feature off, right?
Like how radio waves work.
Yeah, exactly. Yeah, it's similar to that, except that it's not a sinusoid. The carrier wave is not a sinusoid. It's a square wave. Yeah. So so what is the Manchester signal doing exactly here? Well, basically, you're just essentially, if you look at the Manchester signal, it's just a period of high and a period of low and a period of high and a period of low, but those periods vary over time, right? So what the RMT peripheral does is it just gives you a way to program that by essentially creating an array where in that array you just tell it how long it's high, how long it's low, how long it's high, how long it's low, how long it's high, how long it's low, right? And that's all you're doing. You just fill in that array and then you hit go and then it will generate that waveform. What do they call it? Wave shape, right? For you, right? So you don't have to bit bang it, right? So in other words, you have hardware that generates that based on you programming it. So you program that shape with your software, and then the hardware takes care of actually generating it for you. Okay, that's the idea. Then you've got the LEDC. This one is really named, well, they're both named badly because this one, ironically, we're using to control LEDs. even though it's designed for remote controls. And this one, which is designed for LEDs, we're using to control a speaker. So the naming is actually inversed here, right? Okay, so this one we're going to use to control LEDs, basically the same LEDs that control the billboards on Times Square, the Jumbotron billboards, right? And this one we're going to use to play music on the speaker. Now, as it turns out, there is a better way to do this, which is to use the digital to analog converter that is also available on the ESP32s. But we thought it would be cool to use the pulse width modulation to do that. Why? Because that's how it's done in a Class D amplifier. And also understanding this allows you to understand other things that are controlled by PWM, like motors and power amplifiers and other kind of stuff, right? Okay, so basically what this does is this modulates a pulse width modulated signal. We talked about this at the beginning of the semester. It was intended to implement the dimming effect of LEDs, but we're going to use it to play music, right? So that's the idea. Okay, so here's the schematic. So we have the ESP32, and we've got pin 12, and this is created through the circuit board. Pin 12 is going to be the signal that we use for the LEDs. The LEDs are these LEDs that are really cool, these WS2812 LEDs, which I'm sure all of you have seen. They've become quite popular. They're individually addressable RGB LEDs. And then pin 27 is connected to the speaker, but not directly to the speaker, because if you do that, the PWM signal has some high frequency components in there that cause a high pitch whine on the speaker. And also it makes it very quiet, right? So to solve both of those problems, we have a low pass filter here that filters out anything above about 38 kilohertz, 3.8 kilohertz rather, sorry. And then there's an amplifier, an LM386 amplifier. And then there's some other RC circuit, which I'm not sure what the purpose of this is, but then you connect to the speaker.
According to the data
Right.
sheet, it was like for stability of the op amps.
Yeah. It was dictated to do in the data sheet, but we don't understand the concept behind it, right? But basically that connects to the speaker, and the speaker's on the board, right? So in principle, this should allow us to convert a PWM signal to an audio coming out of the speaker, right? Now, there's actually an additional capacitor, and there's also a trim pot that are on the board that connect to this guy. The trim pot is used to adjust the volume. You have to turn it through with a screwdriver. And the big giant capacitor is also connected to this somehow, but not related to this circuit, right? Okay, makes sense. So in total, there are 3 capacitors, 2 resistors, and 1 variable resistor, all associated with this audio circuit. I'm not showing them all here though, obviously, right?
The big capacitor is to remove the DC component from this.
Oh, okay. Gotcha. Okay, all right, so the first thing is how do we actually take control of pin 27 and pin 12? Well, normally you don't have to worry about that because you just say digital write 12, right? Done, right? But that's using the Arduino stuff. We're going to now do low-level programming. So I mentioned all this. These slides actually came from the earlier lecture I did, but I went through it real fast, so I want to take a second look at this. So the ESP32 has a fairly complex infrastructure related to its pins. So the ESP32 has 48 total pins on it. 8 of those you can't touch. They're like power and ground and whatever, something. There's 40 of the 48 are user programmable. And the way that they're usable programmable is you basically configure a mux so you've got a mux that basically controls 228, there's 228 signals in the ESP32 that could be connected to inputs and outputs. But if you just consider outputs, there's actually 190 of those 228 are signals that can be sent out. And there's 173 signals that can be brought in, right? So that's done through something called the GPIO matrix, which is really just a mux. But the reason they call it a matrix is that there's one of these muxes for every one of the pins. Actually, there's two of them. There's one mux for the outputs and there's a demux for the inputs, right? So that's why it's a matrix, is that you've got 40 of these, right? Now, the thing that sucks about that is that means that there are 40 separate control registers used to control these. And so and then there's 40 different addresses. So you have to look up the address corresponding to which one of these muxes you want to control. But to make things even more confusing, there's an additional mux. There's not just one mux you have to set up, but there's two. There's the GPIO matrix, and this is for the output. So if I want to connect one of my if I want to connect one of my 190 signals to an output pin, I have to select one of those 190 signals in the matrix. Then I have to go to this thing called the IO mux, and I have to attach the matrix to the IO mux, right? Because this IO mux allows you to bypass the matrix, the mux here, right? Why? Don't know. Don't understand that. Seems redundant.
The reason is,
right?
certain functions in the ESP30 do need to be like really high speed, like SPI, for instance, because that's how it talks to the flash memory. And so you can just completely bypass the matrix for things like high speed SPI, and it'll just connect straight to the processor itself.
Yeah, so I guess the presumption there is that this has a lower clock than that. I wouldn't expect that to be the case. I would think latency would be the bigger issue than speed, but it could be. Yeah, it's some kind of performance related issue, right?
That's what the two function things are in the IO mux over there, 0 and 1.
Okay, so basically what that means is that you have to set the matrix and the IO mux for every pin. 2 steps, right? The problem is that the IO mux selection is not standardized for every pin. So if you want to connect the matrix through the IO mux, that setting is different for every pin. It's not always the same. And you have to look it up. I don't know why. So sometimes the IO mux is a 3 to send the IO matrix through. Sometimes it's a 1. You have to look that up, unfortunately.
Once we have it looked up and we know what it is for each pin, we can just sort of set something up that remembers that and call that.
Exactly. You just put in your code and you don't have to worry about it again.
I didn't know if it was different for like same pin, different registers based on what part of the transaction we're in or something.
No, it's per pin.
Okay.
There's a table in the data sheet that has the IO mux settings for each of the 40 pins. Okay. Okay, so here's an example of the 2 signals that I'm referring to. So the matrix one is not called matrix. You want to set up the matrix? Don't search for matrix. You got to search for func. But don't search for func 12 because in the manual it's func n. Right? So finding this in the manual is difficult. But in this case, I've say GPIO func 12. Again, func 12 does not appear anywhere in the data sheet. It's always referred to as func n, right? Because n can be 0 to 39. And then there's IO mux GPIO 12, or as the manual calls it, IO mux GPIO n, right, in the manual, or x. Sometimes they use x, usually n, right? Okay, and then here is the select for the mux that routes the 200 some odd signals through the IO matrix. Notice it's 9 bits, 8 down to 0. And down here, the select is 3 bits, 6 down to 5, I think. Yeah, 6 down to, oh no, I'm sorry, 14 down to 12. It's called MCU select, right? So this is a 3-bit select for the IO mux. And this is the 9-bit select for the matrix, right? And they're in 2 different spots. So be aware of that, okay? Make sense? Now you got to use bit twiddling. If you want to change that, if you want to change these bits, you have to read the old values in, replace those 3, and then write back in, right? You don't want to just write, because you don't want to risk blowing away the other bits in there if you just want to change 3 bits. There's always a read followed by a write. Now in my code, I would do a read followed by a write followed by a read, because I wrote my code so it reads back even after I write to confirm that my write worked. Because if you get the address wrong, you can make your code more robust and be able to detect errors by reading the value back and confirming that the write worked. Because one of the things that happens with these control registers is that if you write to the wrong register, chances are it won't even allow you to write to it. But there's no kind of acknowledgement from the hardware. The only acknowledgement you can get back that your write worked is if you read the value back and confirm that whatever you try to write actually worked, right? Make sense? Because otherwise, if you get the wrong address, it just won't work, and then you run the code and it's just bricked, and you're like, well, what's going on? What do I do? Do I run the debugger? No, there's no debugger. No debugger. So what do you do? And this, as you can tell, this happened to me a lot, right? Partly because of this. These addresses are not, the addresses to these are not given to you. All you're given is the base address for the first func, and then you have to do math to figure out what the 12 func register is, right? You do that math wrong, and then you write to it, and then the system just ignores you and doesn't give you any kind of error return or exception or anything like that. It just doesn't work, okay? All right. Okay, so, yeah, so I already mentioned that. Okay, so here's an example. Okay, so these addresses, I put in the lab sheet that you should have a define for each of these addresses. Now, to me, I just automatically did that, but I want to make sure you guys do that. It makes it easier to help you out with your code and to grade the assignments, okay? So this is a requirement that you put these defines. These defines are probably exist somewhere already in the ESP32 header file somewhere, but I don't know where those are or how to access them, so we're just going to rewrite them, right? Based on the manual and the numbers I give you in the lab sheet. I think I give you all these in the lab sheet, okay? And then you can use the reg clear bit, and I don't think we've used these before, have we? No, I mentioned these in class, but we never actually used these. So there is a register clear bit and a register set bit macro. These are provided by Arduino, I believe, or ESP32, somebody. And the idea is that you can just clear specific bits or set specific bits. So in this case, I want to clear all the bits from 8 down to 0, 9 bits. So how do I do that? I take a 1, I shift it 9 bits to the left and subtract 1. That'll give me 9 1 bits. And then the clear will clear all the bits corresponding to those 9 1 bits here. You guys see that?
By the way, there were like 1 or 2, it might have been these, there were like 1 or 2 macros that were like supposed to be in there, but like they weren't, and so I had to write them myself.
Oh yeah, I've got them. I'll get to that. Yeah, the D ports.
Oh yeah.
Yeah.
That's the D part.
Yeah, I'll get to that. Those are in the lab sheet and in the slides. I'll get to those. But just to be clear, these exist. You don't have to define these, but there are other ones you have to define. And then set bit is where I'm setting, in this case, I'm just setting a value in func12, right? So actually, I guess these macros take care of reading the old value, right? And then clearing and then writing back, right? So just to be clear, if you use these macros, you don't have to read the old value out before you modify it, because each one of these macros takes care of reading, modifying, and then writing, right? So reading and writing to the register are encapsulated within the behavior of these macros, okay? Right, any questions about that? Okay. Now, this is what Alex was just talking about. So there are a few special registers that are considered magical D-port registers. I think there's only 2 of them. There's very few. And they're the ones that, I think they start with D-port, right, in the name. If you have a register that starts with the magic name D-port, the prefix D-port, then you have to use these alternative macros to access them, and you have to define these macros in your code. So you can just copy and paste this. Okay? So the way it works is You notice that the read and write are just dereferencing operations, right, with the star fundamentally, and then the set bit and clear bit do the thing I was just describing, where they read and then subsequently write, right? So they read the old value, they modify, and they write the new value back. Okay, so let's talk about the LEDs now. So these LEDs are pretty neat. I think when they first came out, at least when they first were introduced into the maker community, they had a name called NeoPixels. Everyone called these NeoPixels. And then at some point, someone decided that NeoPixel was no longer going to be used, and that name was expunged. When the NeoPixels came out, the idea was that you could get a string of them of arbitrary length, and then you could control individual pixels. And each of the pixels, and when I say pixel, I mean LED, and each of those LEDs had 16 million colors, which seems like a lot for an LED. But what was really happening was that those LEDs were not LEDs, they were 3 LEDs, red, green, and blue together. And what was happening is that you were individually controlling the brightness, probably through pulse width modulation.
Yes.
But that's all done inside the LED, so you don't have to worry about that. So in other words, we're not having to send these LEDs pulse width modulated signals, because that's handled inside the LED itself. Apparently they have a pulse width modulation circuit inside them, right? All you have to send them is a 24-bit RGB value, red, green, and blue, 8 bits each, and then the LED will just turn that color, right? So when these came out, I had this, I was like really shocked, because I was like, what's the limit? My first question was like, how many can we do? Like everyone said, infinite. I was like, really, infinite? I mean, probably there's a limit, right? No, you can put 1 trillion of them and individually address any of the trillion. I'm like, no, Viraj, can you figure this out? Figure out what the protocol is. And of course, he couldn't figure it out. So it wasn't until years later when we developed this lab that I finally figured out that there is a limit to how many. It is not infinitely, but you can put a lot of them, right? So the way it works is they ripped off the Manchester encoding scheme, basically. So the idea is that they wanted to create an asynchronous protocol for these. And it was bit serial asynchronous protocol. So basically they recreated SPI, essentially, right? Except they didn't want to put slave select, and they didn't want to put the clock, right? And they didn't want to have, they wanted to create essentially like a daisy chain, right? Almost like JTAG in a way. But how do you get away with not having clock? That's the question, because even JTAG has a clock in it inside the signal. How do you get away with that? And for that matter, why not have a clock? I don't know, I guess it's an extra wire, right? So how do you not have a clock? So you rip off the whole remote control thing, basically. What you do is you encode a 0 as a specific amount of time that the signal is high, and a specific amount of time the signal is low. And then a 1 has a different amount of time high and a different amount of time low. So what you end up with is basically you have a clock signal in which you've embedded the data, much like Manchester encoding, where you have this signal that's going up and down, not with a 50% duty cycle like a clock, but still continuously toggling, and you've embedded the data. However, it's not like Manchester, in which in a Manchester encode, you take the data and you XNOR it with the clock, right? In this case, you have a table of timings. So the high is 400 nanos, so T0 high or T0H and T0 low is the high and low time for a 0, right? And T0 high, T1 high and T1 low are the high and low time for a 1, right? Now, what happens if you mix the high time for a 0 and the low time for a 1? Well, that's unclear. I don't know what happens. Maybe someone will try that. I guess it would be confused, but I don't know exactly.
Probably just ignore it.
Maybe it'll explode or something. I don't know. I don't know what will happen. But it has to be high. You have to choose the high and low value for each bit, and you have to pair them together, right? Okay? So then you might say, okay, fine, that explains how data. Oh, by the way, how does an LED measure nanoseconds exactly? Well, there's probably there's an internal oscillator, I guess, which means that these guys not only have internal PWM, they have an internal oscillator, which means they have a crystal, a quartz crystal inside every individual. That's crazy, but anyway.
I mean, those are some big LEDs.
Yeah, unclear, but they got a lot of stuff for those. There's a lot of stuff in there, right? They're pretty complicated. But anyway, yeah, they all have a quartz crystal, I guess. But anyway, or maybe a ring oscillator. I don't know how they work. But anyway, so you have a high and a low, and that's how you encode the data. Now you might say, okay, so they all have one input and one output. One input called D in, one output called D out, and you just daisy chain them, right? The way that you individually address them is really clever. When you power up the LED, they start out in a accept state, which means that after they receive 24 bits, they use those 24 bits to set their color. But then after that, they go into a relay state where instead of recording data sent to them, they just pass it to the next one down the chain, right? And then the next one down the chain, once it gets its 24 bits, it goes into its relay state and it passes. So basically, you send 24 bits, the first 24 bits you send in the chain is automatically assigned to the first LED in the chain, right? So the LEDs are addressed implicitly according to their position in the chain, right? That's pretty cool. But then the question then is, well, how do you tell them to change their color? Well, to do that, you set the D in low for 50 microseconds. Now keep in mind, there's a vastly different time scale involved here. These guys are nanoseconds. This guy is microseconds. So the time scale used for the bit encoding is 1,000 times faster than the time scale of the signal that tells them to all go back into their accept state. But even after you put them back in their accept state, they will still retain the color last assigned to them. So when you power them up, they come up, they're dead, they're off. Once you configure them, they go on and they stay on beyond when you reset them until you explicitly reassign the colors to them, right? So in other words, once you turn these guys on, they're on until you either power them off or explicitly go in and reset the color of it, right? Does that make sense? Okay. Any questions about that? Okay.
So what in that code does reset do?
Reset just puts them into an accept state again. So it allows you to reset. It allows you to reset the addressing procedure where you're addressing each one. And now the problem is to call them addressable is not technically true because there's no way for me to change the color of the third LED on the chain alone. It's impossible. Can't be done. You have to change, if you want to change the third one, you got to change the first, second, and then the third one, right? So it's a little bit of a misnomer. They're not exactly addressable. Okay, so we're going to use the RMT for this. So we're going to hack a Manchester encoder to create a WS2812 encoder. So the RMT has 8 bidirectional channels, meaning that we could do input and output, meaning that we could transform the ESP32 into one of these 2812s if we wanted to, but we're not doing that, right? Because that would make them even more expensive, right? So we're just going to use the output channel. This thing has the ability to run on the 1 megahertz clock or an 80 megahertz clock, which are both available in the ESP32. The 1 megahertz clock has a period of 1 microsecond, and the 80 megahertz clock has a period of 12.5 nanoseconds. So we have to use, remember, the coding is nanoseconds. So if we were using the 1 megahertz clock, it would be impossible to do this lab, right? Because we wouldn't have enough resolution to actually send those signals. So we have to use the 80 megahertz clock. And even then, we can only approximate those T0 high, T0 low to multiples of 12.5 nanoseconds, which I don't believe those numbers are multiples. Maybe. No, 850? Is 850 evenly divisible by 12.5? Probably not. So we're not going to nail it exactly right, right? But we'll get close enough. Oh, it is? Oh. Oh.
Yeah,
Oh, wow. Okay. I didn't realize that. Okay, cool. Well, that's good. That works out well then.
That's 16.
Okay, so what is the procedure? So this is the part that's a little problematic, is setting up the RMT. It requires a inordinately long set of steps. So the first thing you have to do is you have to use the dport macros that we gave you to, so what the dport is, so wait, let me back up here and clarify something. So I mentioned that there's about between 200 or so signals that you can connect to input and outputs on the ESP32, right? What are those signals? Those are all the signals coming from all the hardware peripherals, basically. One of those signals is GPIO. So like, you know, in Arduino, when you just say digital write, that's where you just put a constant on the I/O. That's only one of the 200 possible signals that can be connected to those, right? The RMT and the LEDC are other possibilities, right? Now, for whatever reason, all those peripherals, you might say, is there really 200 peripherals on the thing? The ESP32 has 200 peripherals. Yeah, there's a lot. I mean, not 200, because some peripherals have multiple signals associated with them, but there's a lot. But they're all powered off by default. So you got to turn them on. But then that's not enough. You can't just turn them on, because even after you turn them on, they're in a reset state. They're on, but they're in a reset state. Why? That's ridiculous. If you turn them on, you obviously want to put them out of reset, right? But you got to have to turn them on and then take them out of reset. Okay? So those are through the dports, the dport macros and the dport registers. Okay, then with the RMT, so I mentioned the RMT has a memory that's used to program the waveform, right? That waveform comes from a memory, right? A little array. You have to turn that on, even though there's no other way to use the RMT other than having that memory turned on. So why exactly, right? And by the way, Alex, this nearly drove Alex insane, this step, because
5 hours. It wouldn't, my writes wouldn't stick. I was like,
yeah.
What's going on? I finally figured out you can turn the stupid RAM.
This is what I was talking about. Remember I mentioned that I read all my writes back to confirm they wrote? Alex doesn't do that, and as a result, he wasted 5 hours.
I was reading them back when I was doing this, and I was just trying to figure out why they weren't sticking. I was looking all over the data sheet, and I finally found
So that's, he was doing that, and that's how he figured out it wasn't writing. They weren't sticking. So he was writing, it wasn't taking effect. And it turned out that he had to enable the RAM to make them take effect. Now, normally, if I write and it doesn't take effect, my first assumption is I must be writing to the wrong address. So I'm going to, right? That's usually the reason. But in this case, he was writing to the right address. He just didn't turn on the physical RAM that he was writing to, which is something that you've never have to do for any other peripheral on this. Basically, it's unique to the RMT, right? Okay, but luckily we figured all this out for you guys. So you enable it. By the way, the exact address and all that stuff is in the lab sheet. This is just an abstract overview. All the details are in the lab sheet. Okay, then there's a clock divider. So remember that the 80 megahertz clocks gives you 12.5 nanoseconds of resolution, but that might be too much. Actually, I think for remote control, that would be too much, because I think remote controls are slower. But for the LEDs, that's actually perfect, as we just learned, right? So we want to set the clock divider to 1. Now, by the way, some of these, it's not clear to me how many of these are default and how many of these we actually have to set. I think most of these you have to set. Some of them might be redundant because they might be the default when you power it up. But just to be safe, we're going to have you set all this stuff.
There is no default.
Yes, some of them aren't specified too. Like the default is just undefined, so you have to.
Yeah, so it's safer to set as many of these as possible. You should not assume the default. Okay, then you have to turn off the RMT carrier frequency. This is what I was talking about. Remote controls actually have a carrier frequency. If you use if you have an old 1990s TV, they have a carrier frequency, but we're going to turn it off, meaning that a 1 is a 1 and a 0 is a 0. If you have the carrier frequency on, a 1 is not a 1. A 1 is this, and a 0 is flat line, right? Set idle value to 0. this one's really important because remember that the reset, in order to get the LEDs back into their accepting state, you have to have that D in 0 for 50 microseconds or more. If the DN is 1 for 50 microseconds or more, it won't go into reset. So this is actually a way that you would retain, like if you wanted to keep them all into the, you didn't want to put them back in the accept state for whatever reason. But in this case, we're going to set the idle value to 0, and then we're going to specify the reference clock as the 80 megahertz clock, okay? As opposed to the 1 megahertz. Okay, so this is done once. So you guys should have a routine called setup RMT that does this that you'll call once, okay? Okay, then you need another routine that will actually change the value of the LEDs. So what does that actually involve? So basically, the way I had in the lab sheet, I suggested that you do it just to make it easier to help you guys out, because there's many different ways you can do this. The way I did it was I had an array of 5 integers inside the code. And those 5 integers would just have the RGB values of the 5 LEDs, right? When you want to set the LEDs, you have to go in and look at that array and basically serialize it, right? Take each bit out, right? Extract each of the bits. So there's 24 bits for each 5. So there's 24 times 5 bits in total. You have to extract the individual bits. Then you have to take those bits and encode them into the high and low times that I had in that table, right? So if I want to send a 0, I put in 400, 850. If I want to put a 1 in, I put in 850, 400, right? So each bit is converted to either 400, 850 or 850, 400, right? Those numbers are put into the RMT RAM. So the RMT RAM is just an array, and each element in the array is a level followed by a period, right, in the upper 16 bits, and then another level followed by a period in the lower 16 bits, right? Now, Manchester encoding and the WS2812 encoding all go 0, 1, 0, or 1, 0, 1, 0, 1, 0, 1, 0, right? Although technically you don't have to do that. You could put 0 for both levels, but that would be redundant because it would just be a flat line, right? So for whatever reason, you have to put the levels in here, even though it's always pretty much going to be 1 here and 0 here, right? It's kind of pointless. But then the period is the number of clock cycles you want it to be high and then low for, right? Or at the first level, at the second level. Remember that each period is 12.5 nanoseconds. So all you have to do is take the number 850 nanoseconds and divide it by 12.5, and that would be your number for 850, right? Or 400 would be 400 divided by 12.5. You guys make sense? Okay, so the problem though is you need 24 times 5. What is that, 120? You need 120 bits. The problem is you don't have 120 entries in here. You only have 64, right, per light, per channel? There is a way to get more than that, but you have to even do more programming. So you only have 64 entries in here. So the way I did it was I programmed 1 LED at a time. So pretty much what you do is you dump 24 bits into this memory, and then you tell the thing to go. And then you put 24 more bits in the memory and you tell it to go. And that way you'll get the first LED and then the second LED will be programmed, right? You guys make sense? So in other words, when you tell the RMT to go, it's only actually setting 1 LED at a time, right? Meaning, so you populate 24 entries. The problem is that if the software on the ESP32 dilly-dallies for too long, and it takes more than 50 microseconds to go from one to the next, then you're done. It won't work. So how long does it actually take to program this RAM? Does it take more than 50 microseconds or not? Unclear. Well, we got it to work, so apparently it can do it, but we don't know exactly how much of a delay we had in between programming each LED because no one bothered to measure that. right? But it's pretty fat. These chips are pretty fat. They're so shockingly fat. I mean, for someone that used the Atmel, so the quintessential Arduino chip is the Atmel 328P. For anyone that's spent a lot of years using the Atmel 328P, they would look at this and say, there's no way you're doing that in 50 microseconds. No way. No way. It's way too slow. But these chips are so much faster than those that it's pretty easy. Okay, so anyway, yeah, so that's the idea. So the other question is, what happens if you're too fast, though? What happens if the ESP32 is so fast that when you go to program the second LED, the RMT is still working on the first LED, right? What do you do then? So for that, you can use, there's a way to synchronize. There's something here called, there's an interrupt. There's an RMT, channel 0, transmit, end, interrupt, raw, if that isn't long enough. That register will have a bit flag that will tell you when it's done programming one LED. So you can use this to have it wait, in case the chip is so fast that you go to program the second LED before the first one's even done yet. That register will indicate that for you. Okay? In which case you would put a busy loop in there and wait.
Don't actually try and configure an interrupt. That is a huge pain to do at the hardware level. Just pull that bit.
Yeah, this is polling. Yeah, that's a good point. Yeah. It's called interrupt, and we covered interrupts in this class, but it's a misnomer because you're basically saying, are you done yet? Are you done yet? Are you done yet? Are you done yet? That's polling, right? As opposed to let me know when you're done. That's an interrupt. Okay, all right, that's it for that. There's more details in the lab sheet. Oh, by the way, if you find any bugs in the lab sheet, let me know. We've been through several revisions of it, but this is the first time we used it. Okay, so LEDC also can use the 80 megahertz or 1 megahertz clock. Now, the way this one works is, this one's a little bit harder to understand. So the PWM frequency, so you have two components here. You've got the frequency and you've got the duty cycle, right? The duty cycle is the value that you're modulating on the PWM signal. The frequency is, well, it's just a frequency, right? How do you set the frequency? I don't know. I don't think anyone knows. You just pick some frequency, right? If it's too low, like if you have an LED and the frequency is too low, you'll notice like a flickering, right? It won't I actually have this on my adjustable mattress, my adjustable bed has a remote control. And the remote control lights up, but it has the frequency is too low, so it flickers. It lights up and then it goes dim, but as it's going dim, you're looking at it like, what's going? It's flickering, weirdly flickering. What happens if the PWM frequency is too high? I don't know. I don't know if anything happens if it's unclear, right? How do you pick the frequency? I don't know. I don't know how you pick it. But the way the frequency is determined is through a counter. So you adjust a counter, and when that counter overflows based on the clock that you use, that's the period of the PWM signal. So if you have, I think in this lab, the default that we're going to pick is 8-bit. So we're going to use an 8-bit counter, which means the PWM frequency is effectively 1/256th of 80 megahertz. Make sense? So you take the 80 megahertz and you divide it by 2 raised to the power of the number of bits in the counter, and so you don't, in other words, what I'm saying is you don't directly set the PWM frequency, it's indirectly set, right? Actually, it's, this counter is, we simplified, this counter is actually a fixed point counter. Is this the fixed point number?
Yeah.
Yeah, so there's a fraction.
It might have been the clock, it's either the clock divider that goes into the counter.
Oh, yeah, sorry. That's what it is, the clock divider, yeah. Yeah, I'll get to that. So anyway, the point is that I don't think it's important really what you set the clock, the frequency to. It just has to be high enough, but it's indirectly set. The duty cycle has to be but the duty cycle width has to match that counter width, right? Because what happens is that when you set the duty cycle and you have an 8-bit counter and you want to set it to a 50% duty cycle, you have to set it to half the counter dynamic range. So if it's an 8-bit counter, it goes from 0 to 255 and rolls back to 0. So your duty cycle at 50% would be 128, right? Would be half the counter, right? So you have to be aware of, you have to, your counter and your duty cycle work together to determine the duty cycle and the frequency, the PWM frequency. Okay, so to set it up, again, you have to use the D port stuff to turn the LEDC module on and then take it out of reset. Then you have to, now here's the part that's kind of confusing. This confused me. The control registers associated with the LEDs, at least some of them, start with HS timer 0. And you're like, what am I doing? Why am I talking to the HS timer? I wanted to talk to the LEDC. What's going on? It's because they're part of the LEDC are these high-speed timers. Okay, so don't get confused by the naming is kind of confusing. But the HS timer includes the duty cycle resolution that I was just referring to that you should set to 8 bits. And then there's something called high-speed channel 0. Some of the settings are in there, right? So don't be confused if the registers don't actually have the word LEDC in them. You're still configuring that. Okay, so then essentially to initiate an the LED duty cycle, you set the duty cycle, you check that interrupt, there's an interrupt associated with that, you wait for that interrupt to trigger, meaning that you pull it and wait for the interrupt bit to be 1. Then you clear the interrupt, right? So this is the problem with this, is that with the duty cycle, the pulse width modulation, your code has to synchronize with it, right? So your code has to check this interrupt in order so it's not trying to update the duty cycle faster than it needs to be updated, much like the RMT, right? Okay, any questions about that? Okay, so how do you get audio? Well, you just take an audio file, a WAV file, and you save it as samples, and then those samples get matched up to duty cycles in the PWM, and it should play the audio. So we have a script called audio to PCM. This is on Dropbox. Alex wrote this. You put a WAV file in. I don't think it works with MP3s, right? Just WAV file. And then it will generate it basically converts the WAV file into a constant in C, which is stored into array.h. And it declares 2 global variables in there. One is the sample rate, because every WAV files can have different sample rates. And then it has an array of samples. And this array of samples is automatically cropped so it doesn't use more memory than we have on the ESP32. So if this WAV file is too long, it'll just record the first part of it so it doesn't use up all your memory. Yes?
How much memory do we have to work with? Like
How
much
much
time in a song does that actually end up being?
Well, it depends on the sample rate.
Well, we can make the sample rate like garbage.
Yeah, you can
You
make
can
it
still
garbage.
hear megalomania out of it.
But yeah, we have 1 megabyte of flash to work with.
Okay,
So it
that's-
comes out for like 16 kilohertz sample rate. It's like,
Yeah.
30, 45
So
seconds.
don't use anybody employed, just load up like Mario or something. So
Yeah. Yeah. Alex uses Sandstorm. I was thinking we should put that on the Dropbox.
Yeah, I can throw the file up there. and
Yeah.
we can- yeah.
It's a lot like that lab that I did for 313 where I gave everyone that Gamecock image, but you were able to put whatever image you wanted on there if you wanted to put your own.
We haven't done that for like 3 years now. I've never done
Oh.
that before.
Okay, so the lab sheet is, I don't have internet access. The lab sheet is on Blackboard and all the details are there. I tried to put all of the register addresses and their bit fields. So we took pictures of each control register out of the ESP32 technical manual and we put them in the lab sheet. I also put tables with the names and the addresses of all of them so you make your define files. We put some guidelines, coding guidelines, because you know there's a lot of ways you can do this, but I suggested that you have to have an init function for the ESP, our RMT and the LEDC, as well as an update function. And then the update function would be called from the loop function Arduino, right? Because you have to manage them both. You're going to have to. Oh, one thing I forgot to mention. What are we doing with the LEDs actually? So the LEDs, the question is, what do you use them for, right? If you're playing audio, what are we doing with the LEDs? I think it would be cool to create a visualizer, an audio visualizer with the LED. Because remember, those LEDs are 24 bits. We only have 5 of them on the board. But I was thinking to make a level meter where you take the audio amplitude and you use it to light up a certain number of LEDs depending on the amplitude of the audio. And additionally, you can color code them to indicate the level as well. So if you have the more LEDs that are lit up, the more red they'll be using the HSL. The HSL color. No, I didn't use HLL. I used one called Fire. So there's different color maps that are available, right? Depending, there's color maps that translate one input into red, green, and blue, right? One of them is called Fire, I think it is. And so as you increase the value, the color goes from like cooler to hotter, right, is the idea. So what should happen is as the audio plays, the LEDs will show the level, and their color will also indicate the level, right? Should be a cool effect. But audio, you guys probably know this, but audio levels are logarithmic usually. They're in decibel. Decibels are a logarithmic scale. So you have to take the level, which is between 0 and 255 on your PWM, and you have to take the log base 10 of that and multiply it by 20. And then divide that by the 5 levels, 5 LEDs, right? To rescale it to 5, right? And that way, the audio will be on this logarithmic scale because your ears hear audio intensity on a logarithmic scale, right? It's not a linear scale, it's logarithmic. So we want the audio visualizer to also be logarithmic, and that's all described in the lab sheet. But remember, you have to manage them both simultaneously because you don't have an operating system to schedule the code. So you have to schedule the operations in a loop as well. I mean, there is an operating system, but we haven't started using it. Okay, any questions?